Hey guys, so today we're going to talk about conjugation, and conjugation really builds off the concepts that we talked about in resonance. And so we're going to talk about that today, as well as highlight how to identify conjugated molecules and talk a bit about how the visible spectrum and conjugation can interact together. So what is conjugation? Conjugation is basically when electrons are delocalized in these p orbitals here, and they're specifically adjacent, overlapping, parallel p orbitals. And what's great about conjugation is that it leads to very, very good stability. It also results in molecules that are planar, as opposed to having non-flat kind of structure. And they also have a barrier to rotation. So I'm going to write that in right here. So let's take a look at this diagram here and kind of explore this concept further. So here we have a non-conjugated molecule, and this one is a conjugated molecule. And we can tell that by looking at, considering what these p orbitals look like. So this alkene here has only two adjacent overlapping p orbitals to form this pi bond, whereas this molecule has many, more than three actually. So we can see that there's conjugation in this molecule, and these are the p orbitals that I'm kind of quickly drawing in there. You can see that there's some pi bonds forming to make this molecule conjugated. So when we think about the stability of these molecules, let's take a look at this diagram here. These pi electrons in a non-conjugated molecule, this gap here, this delta E, is a lot bigger as opposed to this delta E here, which is much tinier in a conjugated molecule. And so this, if you're wondering, is the HOMO-LUMO gap. So this is the lowest unoccupied molecular orbital. This is the highest occupied molecular orbital. So just to give you some context and figure out where we are in the situation here. So in summary, conjugated molecules allow electrons to travel between three atoms, which is great because now there's more space for them to roam around. And since electrons like to repel each other, they try to get as far away as possible. This leads to, as a result, lower energy pi electrons, and this also increases stability. So conjugation increases stability, causes planarity, there's no rotation around these pi bonds, and this delta E is a lot smaller in a conjugated molecule. So let's talk about what to look for when we are trying to see whether or not a molecule is conjugated. So I like to look for adjacent pi bonds, and I don't really mean something that looks like this, although that could be the case, especially if you have something like carbon dioxide, for example. But I mean something more like this, where you have kind of this nice kind of spacing between the double bonds. So it's kind of alternating, I guess. But in a way, they are adjacent to each other. So that's what I look for. I also look for lone pairs between pi bonds, empty p orbitals, as well as any half-filled p orbitals. Things like radicals, for example, can count towards the conjugated molecule. So let's take a look at this molecule here. This molecule has resonance, which I have indicated here with these arrows. That's not really relevant here, but I wanted to kind of include it as kind of a refresher and see how a molecule with resonance could be conjugated. So let's see. This has a empty p orbital on the carbon, but as I mentioned here, atoms with empty p orbitals do count towards conjugation. So this has three overlapping and adjacent and parallel p orbitals, so this molecule is conjugated. Let's take a look at this one. We have this benzene here, this benzene ring. So here we have conjugated p orbitals. We also have more conjugated p orbitals going this way, so it doesn't end just over here. It continues this chain all the way over here. So this one has 8 conjugated p orbitals. And then let's take a look at this molecule last. This one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 conjugated p orbitals. So it's really good to kind of look for these pi bonds. They're a really good indicator of conjugation. So let's talk little bit about conjugation and color now. So I'm going to direct you to this diagram here where we have butadiene and octatetraene. And this molecule has much more conjugation, as you can tell by there's, more overlapping p orbitals here, as opposed to this one, which has less conjugation. So as I mentioned before, the homo-LUMO gap in a less conjugated or non-conjugated molecule is a lot bigger than the homo-LUMO gap for a molecule that is conjugated. So let's say that a photon of light comes in and strikes these molecules here, and these electrons in the p orbitals get super excited and they jump up to the next lowest unoccupied molecular orbital. And something important to note here is that the photon of light that comes in and strikes this molecule, the energy of the photon actually is equivalent to this energy right here. So that being said, when you have a more conjugated molecule, you of course have that lower homo-LUMO gap, you have a lower delta E, which means that since these photon energies are the same as the energy of this gap, it absorbs a lower energy of electromagnetic radiation, and this includes the visible spectrum, which is what we're really concerned with here. And something that I want to highlight really quickly is this formula. In physics, you'll kind of talk about it, but you also talk about it in OChem as well, and just chemistry overall. But this is the delta E over here. This is Planck's constant, which is a constant value that doesn't change. And then here we have the frequency. So delta E and the frequency are directly proportional. So a decrease in this energy means a decrease in the frequency. So this relationship is important to know, especially when considering light. So just make sure you understand it. And a lower frequency actually corresponds to a greater wavelength of light. So as we kind of talked about, more conjugation absorbs basically a longer wavelength of light. And we know this basically because it looks more kind of like this, as opposed to something with a much higher frequency, a much higher energy, and a much shorter wavelength. So more conjugation, longer wavelength of light, lower energy, wavelength of light as well. So let's look at retinol and beta carotene here and identify what potential colors it could absorb as well as what colors it could appear to be. So looking at retinol, we see that there are how many conjugated p orbitals? Looks like there are 2, 4, 6, 8, 10 conjugated p orbitals. And then beta carotene, let's look at this part over here just to highlight these are not conjugated. And you can tell that because this area does not have a p orbital, this carbon. So make sure just not to go too fast and maybe count something that doesn't exactly apply to the conjugated molecule. However, this one does. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 19, 20. So beta carotene has 20 conjugated p orbitals. So beta carotene is more highly conjugated than retinol is. And that being said, since retinol has less conjugated p orbitals, it absorbs a higher wavelength of light. So it actually absorbs in the violet area of the visible spectrum. And as a result, it appears the opposite color. So it actually appears yellow. And beta carotene, on the other hand, since it's more highly conjugated, absorbs a lower energy wavelength of light. So it actually absorbs in the green-blue region of the spectrum, and it appears the opposite color, which is orange. And beta carotene is actually it's what makes carrots orange. So that's kind of how I remember this whole relationship here. So that's kind of the gist of what you should know for conjugation. And thanks for listening, guys.